Welcome to Manufacturing Methods. Today we'll be talking about engineering materials. We'll start with the topic of metals. One of the first three topics we'll be covering, which the following ones are ceramics and polymers. So metals is one of the most important engineering materials in engineering because metals can satisfy a wide variety of design requirements. They're very strong, have very high strength, high stiffness, and can be used for a wide variety of applications in aerospace, mechanical, and other civil systems. The manufacturing processes by which these are shaped into products, there's been so much work done in the area, has been refined over the years that it's a very good process. And engineers understand metals because there's extensive experience with them. Some metals are important, and there can be pure elements like gold, silver, copper. Those are fundamental metals, and we call them pure because that's the only composition of these metals. However, most engineering applications, just using gold, silver, and copper by itself may not give you the properties that you may need. So to achieve that, it requires to enhance these properties by obtaining something we call alloying. So by alloying components, it is possible to increase the strength, hardness, and other properties compared to pure metals. So what is an alloy? It's a mixture of two or more elements, and by having two or more elements, you can achieve an alloy, and at least one of them should be metallic. There's two main categories that are discussed when it comes to alloy. The first one is a solid solution in which an alloy, which is one of the elements, is dissolved in another to form a single phase structure. So that's an example of cementite, for example. Then you have something called an intermediate phase, where you have an amount of the dissolving element in the alloy, and it exceeds the solid solubility limit of the base metal. And so the phase that forms is a phase that forms in the alloy. So in some alloy compositions, the intermediate phase in this case is mixed with a primary solid solution to form a two-phase structure. In this case, you can achieve pyrrolite, which is a mixture of cementite and ferrite. So again, two main categories. The first one is a solid solution with an alloy in which one of the elements that you have is dissolved into another that forms a single phase structure. Then you have the intermediate phase when you have the amount of the dissolving element that we talked about in the alloy, and that exceeds the solid solubility limit of the base metal. So then phase forms in the alloy. Okay. Now, so because we're talking about alloys, it's important to understand phase diagrams at the top level. And you can go deeper into a material science class. This is not a material science class, however. The purpose of this course is to show you that to achieve optimal manufacturing of components, you can design materials to give you the performance needed for that. And to do that, you can alloy metal to then get the enhanced properties needed for the manufacturing process and design considerations. So phase diagram is a graphical mean of representing the phases of a metal as a function of the composition and temperature. And I'll show an example. A phase diagram for an alloy system consists of two elements, and usually we look at this at the atmospheric pressure. We call this a binary phase diagram. Other forms of the phase diagram are discussed in the textbook of the course. So there's also a chemical composition that needs to be discussed. So the overall composition of the alloy is given by the position the overall in the horizontal axis. We'll talk about that. However, the compositions of liquid and solid phases are not the same, and we will see that. These compositions can be found by drawing a horizontal line at the temperature you're interested in, and then where that line intersects the solidus and liquidus indicates the compositions of solid and liquid phases, respectively. We'll look at examples. So here is a phase diagram of a copper-nickel alloy system. On the x-axis, what you see here is a percentage of nickel. Okay. On the very left, you have 0% copper, 0% nickel, and then towards the very right, you see 100% nickel. So towards the left, you have a copper dominated behavior. Towards the right, you have a nickel dominated behavior. So the solid solution here can be determined through this diagram. On the left side, y-axis here, you have the temperature in centigrades, and that's translated also in temperature in Fahrenheit on the right side. So when I look at this diagram, you can determine what composition levels and temperatures can result into what phase you may have. So this zone here is a solid solution. Here at the top, you have a liquid solution. Somewhere in between, you can have a liquid plus solid solution, and then that will be required to determine the phase in the system. So now let's look at how we will determine the percentage composition for these materials. So what you're going to do, you're going to, for example, I want to determine the proportion of liquid phase present. And so what do I do? I look at taking C here. So say I'm looking at 50%, and I'm looking at this particular temperature. You'll take C here, and then where it intersects here, S, we call this the solidus, this line here. So that CS here will be divided by plus CL. So this length here at the bottom. And that'll give you the liquid phase present for the material. And then you can then determine the S phase proportion. You can either take the 1 minus of this, or you can go here and take these ratios, CL divided by CL plus CS, to be able to get the phase, the solid phase present of that material in the alloy. So the example that I just gave can be shown here at 50% nickel here, 50% nickel, and at temperature 1260 degrees centigrades. Here you draw that blue line and you have the 50%, and then you can now determine what percentage liquid, what percentage is solid. And these two should add up to 1. We can also, I had shown this earlier, you can also look at the tin lead phase diagram. And we discussed this already. Here in this zone, you have a dominated behavior of solid. Here you have primarily dominated by the lead system. And then on the beta here, you're dominated by a solid solution lead in tin. And here's solid solution tin in lead. So what you're looking at then here is a combination of solid solution tin in lead that's in liquid form as well. And then here you have solid solution lead in tin that is in solid solution as well and liquid. And then here you have liquid. So there is something called the eutectic composition where it can go from solid, and that occurs at 61.9%. Tin, you go from solid to liquid suddenly above this temperature here of 183 centigrades. But elsewhere, you can get other phases occurring. So I covered this before, but it's good to review. The eutectic temperature is one where the melting point of the eutectic composition occurs, and the eutectic temperature is always the lowest melting point for any alloy. And you can see here that this point is the lowest temperature at which melting can occur, because at any other point you're going to be going along these lines here. The word eutectic is derived from the Greek word eutektos, which means that's easily melted. So when I look at an eutectic alloy, which is one of them could be based on iron, that's one of the oldest metals known to men. Ferrous metals of engineering importance are alloys of iron and carbon. These alloys can be divided in two groups, steel or cast iron. Together, they'll constitute approximately 85% of the metal tonnage in the United States. So let's look at cementite in the iron-carbon system. So at room temperature under equilibrium conditions, iron-carbon alloys form a two-phase system at carbon levels, even slightly above zero. The second phase that you may have in this system is Fe3C, also known as cementite. And cementite is an intermediate phase we talked about earlier, which is a metallic compound of iron and carbon that is hard and brittle. So let's go back and review that really quick to make sure we didn't go fast. An alloy, there's two main categories: solid solution, where you have an alloy that gets dissolved into another, and that forms a single phase structure. The intermediate phase is when you have an amount of the dissolving element in the alloy that exceeds the solid solubility limit of the base metal. A phase forms in alloy in this case. I can take the intermediate phase and mix it with a primary solid solution to form a two-phase structure. And that's sort of what we're talking about right now. That third category there. And so here we're talking about cementite in the iron carbon system. So in the second phase that we're talking about here is cementite. So now here's a much more complex diagram, but the concepts are the same. Here you will have iron on the very left, carbon on the very right, and this is a percentage of carbon. At this level, you have 100% cementite at this point here, this line, and you can see here that the phase diagram for this iron carbon system is up to about 6% only. And to get to a from solid here, right here, which we call perlite, all the way up to liquid, you have to traverse a number of temperatures. I can also achieve different phases in these materials depending upon the percentage carbon, but also the temperatures. So iron has been used as a commercial product in a lot of different applications. Electrolytic iron, which is the most pure at about 99%, has been used for research and many other purposes where the pure metal is required. You also may have seen ingot iron, which contains about 0.1% impurities, rare impurities. And that's used in applications where you need a high ductility or corrosion resistance. The other one that you may have seen quite a bit is wrought iron, which contains about 3% slag, but very little carbon. And the nice thing about wrought iron, it can be easily shaped by hot forming operations. So by applying hot temperatures, you can form it, and we call that forging. There's also the solubility limits of the carbon in iron. So the ferrite alpha here, that phase alpha, can dissolve only about 0.02% carbon at 723 degrees. And you can see that here, there's 723 degrees, and then the alpha phase is over here, and you can see it can only dissolve about 0.02% carbon. Then you have the austenite phase that can dissolve about 2.1% carbon. And you can see that here because this point right here is about there. And that's at 1130 degrees C. And then the difference in solubility between alpha and gamma provides opportunities for then you be able to strengthen a material by heat treat. So the point of me showing this phase diagram is to explain to you that we can take advantage of this understanding to heat treat materials to increase their performance in various applications. So in this case, the alpha phase here, this alpha phase here, and the gamma phase, that difference in solubility here provides significant opportunities to increase the material strength. So now we can look at steel and cast iron and define that using the phase diagram. If you're in the percentage carbon over here, then we will call this steel. So again, to get to a liquid phase, you need to transverse quite a bit of temperatures to get there. And then for cast iron, you're looking at higher percentage constitutes to be of carbon to be able to get to these cast iron levels. Cast iron can be achieved anywhere between 2% to 5%. Steel and cast iron can also contain other alloying elements. And then what are the eutictic and ectoctoid compositions? For eutictic composition of this system, you can see here that occurs about here, 1130 degrees C. And then for your eutoctoid composition, you're looking at more at a 0.8% carbon, and that's when that happens. So the phase changes between alpha and gamma at 723 degrees C. So iron and steel production. Iron making is very important. It's used extensively. I'm going to touch a very high level. Iron is reduced from its ores, and steel making, in this case, is developed by taking iron and refining that to obtain a desired purity and composition alloy. Okay, so continuing on here, looking forward here. So iron making is typically done in a blast furnace You have a blast furnace where you have a refractory line chamber with a diameter that goes between 9 meters and 11 meters and will typically be very high, like 125 feet, which is like about 10 stories high. And to produce iron, you need to have a charge of ore and a little bit of scrap of iron and steel. You may need coke, limestone, and those are dropped in the top of the blast furnace. And then you're going to have hot gases like hydrogen and steam and other fuels that are forced into the lower part of the chamber at very high rates. I'll show a picture here. This is your refractory lining, and this is your steel shell. You have your hot blaster coming through here, and then you have your hot iron throw here. You have your slag, your iron notch. The molten iron is here. In this process here, we'll have then now layers of iron, ore, coke, limestone, and then here from the top down, like I said before, you're going to have from the top, you're going to charge it with ore. And that process then is going to through this furnace, and you can see a picture here, top left, will then generate the iron making process required. And by the way, you can get limestones from like caves, and it's going to look. So, what are the proportions of raw materials? You have approximately 7 tons of raw materials that are required to produce 1 ton of iron. So, it's a lot of material. 2 tons of iron ore to start, and you have 1 ton of coke. These are the percentages that you need to be able to get there. Half ton of limestone, and 3.5 tons of gases. This combination is what is needed to make that process work. A significant proportion of the byproducts are then recycled, so that's great because you can. It's an efficient process. So iron from the blast furnace. So iron can be tapped from the blast furnace, and further requirement is going to be needed for the cast iron and steel. A furnace called cupola is commonly used for converting pig iron into gray cast iron. For steel, compositions must be closely controlled and impurities have to be brought to very low levels. So steel making has been around for a long time, mid 1800s, and there's been a number of processes that have been developed for developing steel. The two most important processes that exist is a basic oxygen furnace, BOF, or electric furnace. Both are used to produce carbon and alloy steel. So both are used quite a bit. And here is your basic oxygen furnace. It accounts for about 70% of the production of steel in the United States. Typically, some of these systems are about 5 meters inside diameter. And then here you have your molten steel. You have your steel scrap and lime, the molten slag, you have your tap hole, and then here you have the water cooled oxygen, and this is going to now with this tap hole produce a flow and allow for the development of steel. Here's a process sequence. Number one, you will be charging the scrap. Then you have the pig iron being dropped in here. Then you'll apply a blowing process to that. And then you're going to tap the molten steel and add your additives in there. And then you're going to do the pouring of the slag. And that cycle time from tap to tap is 45 minutes. Electric arc furnace can also be used for steel making. Scrap iron and scrap steel are the primary raw materials here. It'll get you to better quality steel if you were to use this, but it's very high cost per ton compared to this process here, the buff. So in this process, you have a molten steel, you have a refractory lining, you have an electrodes that charge, you have your roof, and then you have your oxygen in here. And then by tilting this contraption, and then you'll be able to then pour the material. There's another process, which is casting processes in steel making. These are still produced by BOF or electric furnace, but they're solidified using casting processes. So here you have your mold, here's your stool, and then here's where you drop your cast steel, and then that'll be the process of casting the material. Steel is an alloy of iron that contains about 0.2%, 2.1% carbon by weight. We talked about it. Often it will include other alloying elements. We talked about that too, like nickel, manganese, chromium, and molybdenum. Steel alloys are typically grouped into four. So you'll have four types The first one is a plain carbon steel, where carbon is the primary alloying element. The low alloy steels, where you have iron and carbon alloying that contains additional alloying elements, usually less than 5%. Stainless steel, which has a principal alloy elements, and that's about usually greater than 15%. And then nickel is another ingredient that's added, and that's added to increase the corrosion protection. Also, these materials are very ductile. Then you have tool steels, which are used for tooling. They're highly alloyed, they're heat treated, and they're usually used for cutting and dies and molds. They need to be very strong and stiff. For cast irons, we also covered this, but the composition here makes them very suitable for casting metals. Now, the tonnage of the cast iron castings is several times that of many other cast metal parts combined, and the overall tonnage of cast iron is second only to the steels among many metals. So here we're talking about this zone here, the red zone. Here we're talking about the purple zone. And so then we have the non-ferrous metals. These are metal elements and alloys. They're not based on irons. So many important non-ferrous metals that come to our mind are aluminum, copper, magnesium, nickel, titanium, zinc, and many other alloys. Although non-ferrous metals are not as strong as steels, they are non-ferrous alloys that are very corrosion resistant, and the strength to weight ratio is really nice, which makes it very competitive with steel. The steel is very heavy. Yes, it's higher strength, but if you can go with something lighter, it may be useful. Many non-ferrous metals have properties other than mechanical that really make them ideal for many applications where steel may not be the best option. Examples is aluminum and magnesium. These are very light metals, but very strong, and you will see them a lot in aerospace applications, mechanical. Both elements are abundant in earth, which is very advantageous. You have aluminum, a lot of aluminum on land, and the magnesium tends to come from the sea. Now, neither of these are easy to extract from their natural states, but we have a lot of it. To produce aluminum, you have to start with the principal ore, which we call bauxite. Now, this tends to be mostly a hydrated aluminum oxide, and to extract aluminum from bauxite, you have to wash and crush the ore, to very fine powders. There's another step called the Bayer process. That process converts bauxite into pure alumina. And then you have electrolysis, which is where you separate the alumina into aluminum and oxygen gas. So about you need electricity obviously for this process to produce about 1 pound of aluminum from alumina. So what are the properties of aluminum? They have very high electrical and thermal conductivity. That's one thing. Excellent corrosion resistance, very ductile metal, which is very nice for forming. And the pure aluminum tends to be very low strength, which is why you need to get alloyed and heat treated so they can compete then with steels. Otherwise, it will give you lower performance. The other nice thing about aluminum is that there is no fatigue limit. You can see here that in the SN curve, you have excellent performance for these materials. And this is your red curve. The y-axis is the number of cycles. Sorry, the number of cycles is in the x-axis, and the y-axis you have the stress level that's applied to the cyclic coupon. And so the red here shows that there's no fatigue limit. You have a magnesium, which is there's seawater, contains about 0.13% of this. And this is a source of most commercially produced magnesium. To be able to extract magnesium, you have to take seawater, mix it with a milk of lime and calcium, and that's going to result in a reaction. They'll precipitate magnesium hydroxide. But once it settles, then you can remove the slurry, and that slurry will then be filtered to increase the content of this material, the magnesium hydroxide. The slurry then is mixed with another process called hydrochloric acid, which then reacts with the hydroxide, and that allows the formation of magnesium much more concentrated than the original seawater. Then now use a new process. This process is electrolysis, and then we use it to decompose salt into the magnesium and chlorine gas. So by using salt, you're able to then decompose it. The magnesium, then you can take it and cast it into ingots and then use it for further processing. And the chlorine that's created here can be recycled to form more of the magnesium earlier. Magnesium is used quite a bit. It's the lightest of the structural metals. Is available both in wrought and cast forms, relatively easy to machine, and in all processes of magnesium, small particles of the metal oxidize rapidly, and care must be taken to avoid fire hazards. So the nice thing about these magnesiums is that it's easy to machine. You also have multiple ways you can get this material wrought or cast. So very beneficial. So property of magnesium, is relatively soft. It lacks sufficient strength for a lot of applications, but if you alloy it and you heat treat it, you can get very similar properties as aluminum. There is a lot of advantages, and it has been used in aircraft and a lot of military components. Now, copper is one of the oldest metals that you may have known. Very low electrical resistivity and is widely used as an electrical conductor as a consequence. You will see that used quite a bit. Also, is a great thermal conductor. Now, the thing about copper, which is used extensively in electronics, it is corrosion resistance. And because it's one of the noble metals, gold and silver are also known as noble metals. In ancient times, copper was available in nature. Today, copper is extracted from ores, or this particular ore is crushed, concentrated by flotation, and then smelted. And what smelted means is you melt it or fuse it, and that often requires a chemical reaction that allows you to separate the metal from the ore. That results in a copper that's about 98 to 99% pure. You can use electrolysis to get a higher purity level, and that's usually done for commercial use. So copper alloys strength and hardness is relatively low. That's the problem with them. To improve their strength, copper is typically alloyed as well. So you have bronze, which takes an alloy of copper and tin, 90% copper, 10% tin, widely used today. You can see here a picture on the top left of the Bronze Age. Brass, which is alloying copper and zinc. You've seen that in musical instruments. And then if you need very high strength materials, like for a lot of aerospace or mechanical applications, the high strength alloys, beryllium copper, which can be heat treated to high strengths and they are used quite a bit in springs. Now, this material, nickel, is very good material. Similar to iron in a lot of ways. The modulus of elasticity of this material is similar, has great magnetic properties. Now, the difference with iron is that nickel is very corrosion resistant, is very strong material, and it has high temperatures resistance. Properties for nickel are far superior for high temperatures and are used quite a bit in engines. To get to nickel, you have to extract nickel from an ore, usually called a pentallidite. And you can see the composition there. This ore is crushed and ground with water, then use flotation again, as before, to separate the sulfides from the other minerals, because you have this S here. The nickel sulfide is then heated, and then you'll burn out the sulfur. Then you'll do smelting like I discussed before, and then with additional refinement, you will get a high concentration of nickel sulfide. And electrolysis is then used to recover high purity nickel from that. So nickel alloys of nickel are commercially important, and they're used in a lot of different applications, and we call them superalloys. A lot of superalloys are based on these nickels because they work for high temperature performance, great corrosion resistance, and so superalloy is the appropriate for them. Applications: stainless steel alloying ingredient there, plating metal for steel, and applications like engines, like I said before. Titanium and its alloys, you have abundance of those. 1% of the earth crust is shows why. Aluminum is about 8%. Density of titanium is between aluminum and iron. And in aerospace application, it's used quite a bit because it's lightweight and has a great strength to weight ratio that you can exploit. For getting to titanium, you have to start with an ore of rutile, and you can then use ilmenite, which is a combination of the two ingredients here that you see. To recover titanium from the ore, you have to take this system and convert it to titanium tetrachloride by reacting with chlorine gas. And then that tetrachloride is then reduced to metallic titanium by reaction with magnesium, which is known as the Kroll process. The resulting metal is then used to cast ingots of titanium and its alloys. The properties of titanium, coefficient of thermal expansion is relatively low among the many metals, so that's very nice if you want to see high temperature excursions and you want to keep something dimensionally stable, this is not a bad material for it. It's stiff and strong compared to aluminum. It retains great strength at elevated temperatures, but however, pure titanium is reactive and it can produce a lot of problems. So at room temperature, titanium forms a thin adherent oxide coating, which is kind of nice because it provides corrosion resistance. Titanium is used a lot in engines as well. You can use it at high temperatures up to 1000 degrees. Provides great strength weight ratio. It is in the commercially pure state. Titanium is used for a lot of corrosion resistant components, such as marine components and prosthetic implants. Alloying elements are also used in titanium with titanium, and that will include aluminum, manganese, tin, and vanadium. Zinc has very low melting point, makes it very nice because you can make a lot of castings out of them. Also provides corrosion protection when coated onto steel or iron. And the term used typically here is galvanized steel, which refers to steel coated with zinc. It's widely used as alloy with copper, like brass, for example. The production of zinc, you start again with a principal ore, typically, is a zinc blend or sphalerite. Due to the small percentage of sphalerite in the ore, you must concentrate that. First crushing it, then grind it with water to clear the slurry. You take the slurry, agitate it so that the mineral particles float to the top. You can skim that off. The concentrated now sphalerite is then roasted with heat, and then you have zinc oxide is then formed from the reaction there. Zinc is then liberated from the ZnO zinc oxide by electrolysis or thermomechanical reactions, chemical reactions. Lead and tin are often used together due to their low melting points, and we use them in soldering alloys. Lead has dense and low melting point, very low strength, low hardness, high ductility, great resistance. It's used a lot in a lot of applications like solder, bearings, ammunition, many metals, X-ray, shielding, storage batteries, vibration damping, and tin also has low melting point, very low strength, low hardness, and good ductility. Is used quite a bit, and you'll see them using tin cans, for example, for storing food. You then have other materials called refractory metals. These metals are capable of enduring very high temperatures. Some of them are molybdenum and tungsten. Other ones you may see others niobium and tantalum. These materials are used quite a bit in rocket applications and many other applications where heat may be important. Molybdenum has properties with a have very high melting point, 2623 degrees C, very stiff, strong, good high temperature strength. It can be used as a pure metal, but it's typically alloy. Applications include heat shields, heating elements, electrodes for resistance welding, dyes for high temperature work, and parts of rocket and jet engines. Also widely used as an alloying ingredient in steels and superalloys. Tungsten also very high melting point, one of the densest, also the stiffest, and the hardest of all the pure metals. Quite a bit used, and it is heavy, but you'll see it used in incandescent light bulbs, parts of rockets and engines, and also electrodes for arc welding. Also widely used as an element in tool steels. You may see that. You then have another group of elements, metals, gold, silver, and platinum group. They belong to the noble metals because of chemically inert, and they're available. It's available in very limited supplies, used throughout the whole history of the United States and the world for coins and for underwriting paper. Also used quite a bit in jewelry. You all very familiar. Very high density, good ductility, high electrical conductivity, corrosion resistance, expensive, but moderate melting temperatures. Superalloys are high performance alloys, and they're designed to meet demanding requirements for strength and resistance to surface degradation at high temperatures. I discussed that already. Many superalloys contain substantial amount of three or more metals, and they're commercially important because they're very expensive. Why superalloys are important? They're used, you can see here in engine. Room temperature strength properties are good. They may not be outstanding, but at high temperatures, this material provide amazing tensile strength, hot hardness, creep resistance, corrosion resistance at very elevated temperatures, and operating temperatures often in the 1100 degrees C. Applications include gas turbines, jet rockets, steam turbine, nuclear power plants, and so forth. So, manufacturing process for metals. Why is all this important? It's important because these metals are shaped by all basic shaping processes. And understanding their properties, understanding how these materials behave, it allows us to understand what processes can be used in the manufacturing. Metals are shaped by all kinds of processes: casting, powder metallurgy, deformation, material removal. In addition, metal parts are joined to form assemblies like welding, brazing, soldering, and mechanical fastening. Heat treating is used to enhance properties. We discussed that before. And then for the finishing processes, like electroplating or painting, it allows you to provide better appearance of the metals and provide corrosion protection. Thank you for your attention and have a great day.